Hello guys, my name is Christian Flodin, and this is the first video in a series how to design and program your own state-of-the-art game engine. We're going to do this using C, C++, and a number of platform independent libraries. But this first tutorial is not going to have any programming. We're just going to talk about high-level architecture and design, how to design your code. So first of all, I'm going to define what I mean with state-of-the-art. I'm not going to make an engine that is the fastest one, nor the most graphically capable engine. With state-of-the-art, I do mean a game engine that is flexible and remains flexible and easy to extend while adding more and more features to it without causing a huge monolithic structure to form and just create a huge mess. I've been looking for some sort of videos about this on YouTube already, but to my surprise, I actually didn't find any that had the standard that I would expect. I saw a couple of videos about game engine or game architecture and design, but they all either went to high level or low level. They didn't really talk about the architecture in a way that I understand it. So that is why I creating this series. So I've been looking and using game engines for a quite long time now. I've been using Unity for a couple of projects. In some of the games I ran into some issues with Unity's way of dealing with things. So I started to look at other game engines such as CryEngine and UDK. And while they're all good engines, they also come with their weaknesses, and I really felt that I really got the impression that they were all a bit monolithic in their design. So I decided to roll my own engine. So while I'm doing this, I'm going to create basically tutorials while I'm doing it to share with you guys on YouTube. So what we are looking at here is the 3-tier architecture. It's a design that popped up about 20 years ago, and what it means is that you split your application into 3 tiers: the presentation tier, the logic tier, and the data tier. And they all work together to achieve something, but they are also independent from each other and separated and isolated. For example, all data goes into the data tier, and all logic decision making goes into the logic tier, and everything that renders stuff shows something to another system or a user is isolated in the presentation tier, which kind of creates a good independent system. For example, you can remove the data tier, which means that you cannot really have show anything to the user because there's nothing to show. Imagine a big database of movies. All the movies would be in the data tier. The logic would probably select a couple of them, and the presentation tier would display those to the user. If we remove the data tier, the logic and presentation tier would still operate, but since there are no movies to show, the user wouldn't see anything. Same with the presentation tier. If you remove the presentation tier, the program would still function. It would still be able to access videos and similar, but the user wouldn't be able to see anything. So the reason of doing this is you want to isolate different, you do want different tiers, and you want to isolate their code. So for example, anything that has to do with the presentation, for example, you might have a library to display some text or some images. You don't want that to leak out to other parts of the system. You want to keep it isolated within the presentation tier. This does not only make the application overall much easier to understand, it makes it also easy to debug. For example, a bug in that relates to the graphics, there is no chance that it can affect anything in the logic or the data tier, because they are completely separated. So what I mean with completely separated is basically an observer pattern. You can of course achieve this through other means, but we will talk about the observer pattern later on. So let's look at the model view controller. It's a system that is even older, originated basically since from the 60s or the 70s, and it's been around for quite sometimes like 30-40 years. It has recently become very popular within web development, and what it's basically doing is that you have a user here that generates input which is handled by the controller, and the controller receives those and changes a model, and the model just keeps the data, and whenever the data changes, the view gets notified about this and renders whatever stuff is in the model. So most people, especially within web development, always refer the model to a database, but that does not need to be true. The model can be pretty much any type of persistent data that lives in your application. For example, a game entity. So how do you actually make these parts communicate and work together without letting them be dependent on each other? So we're going to look a bit at the observer pattern. So imagine you have a model that stores a lot of data. So our subject here is our model, and it has a function to register an observer. So something can call this function and say register me, and each time the model does any changes to its data, it will go through all the observers and notify them about the change. It doesn't know what these things are, it just knows that they are observers. And for example, here in concrete observer A, this could be the view that implements this interface and register itself on the model, and as soon as something changes, it will get notified by this notify function. But the model here in the subject actually doesn't really know that it is a view that it is calling. It just knows it's an observer. So this is how we keep things working together without actually knowing what, without being dependent on knowing the other parts of the system besides the interfaces of the observers here. So what we're going to do is a bit of mix between this three-tier architecture and the model view controller concept. You can see that this one is very similar to the model view controller concept, but according to the three-tier architecture, it does separate the logic from the rest of the system. So we're going to have the controller receiving input from the player or the network. It translates this raw input to events, to game events, which is sent to the logic, and the logic does change stuff in the model, and the view renders whatever is in the model. And in the model, in our game engine, we're going to store like game entities. So we're going to change position and stuff inside the model, and the render and the view will just render whatever stuff is in there. So let's talk a bit about game objects. In most common, when you see people talking about game objects, what they're doing is like they're doing like this. They basically have this big game object that has an ID, it has a model, it has a name, it has the hit points, the scripts, and mesh objects, and script files, and whatnot, right? So for example, when this is deleted, you not only lose its capability to be displayed, you lose all its state, its name, and its HP, and you lose everything. So if you ever have played a game which requires you to restart the game because you changed the resolution or something like that, it means that this is what they're doing, because they need to restart basically the rendering part. But since the rendering part and all the data is kind of in the same object, they will lose all the game state while doing this. So they have to restart the whole game to just change the rendering. So this is not something we're going to do. We're going to do it like this. We're going to do like this. We're going to have a model, view, and a logic, and we're going to create 3 separate objects that are all associated with one unique ID. So you can see that the model stores all the data. It has the model file. It doesn't load the real mesh. It just says the mesh or the model that you should use is this file path. And the name of this game object or game entity is Ace. It has 10 hit points, and it should load this logic script in scripts_play.script. And the view is another object with the same ID, but it actually has the loaded mesh or model file that is used by a rendering engine of some sort to display it on the screen. And the logic would actually have access to the script file and run the logic. So that's about, this is how we're going to treat game objects or game entities in our engine. So another benefit of doing this is, for example, imagine you want to go multiplayer, right? You have 2 computers, computer 1 and computer 2. You start the application as usual on computer 1. Then you launch another player on computer 2. The difference is that the computer 2 doesn't have a logic. It connects, the controller through the network connects to the logic on computer 1, and the logic then when it makes changes both to its own local model and to the remote model in computer 2, which basically means that you have implemented a multiplayer functionality. You can use this for different kind of things. If you want a server, for example, you can just remove the view and you can let different other computers connect to it, and you have a server and you have clients. Or if you want to connect a number of observers, for example, you have 2 people playing, but you want 10 people being able to observe the game, you can just create a view on those observers and hook them into the remote model, and you would be able to pick and choose and connect different parts to each other to achieve those things. So this is how we're going to structure our game engine, and this is the end of the first tutorial. So next tutorial we are going to start implementing this using Visual Studio 2010 and basic C++. Stay tuned for the next video.